Okay, this is multiple choice, section 3A. Which of the following defines a function, f, which the opposite of x is equal to the opposite of the function? This is a definition for an odd function, so you're looking for functions that are odd. This is an even function. One of the rules you can think about when you have a monomial means one term. So this is an example of a monomial. If I did plus 2, that's no longer a monomial, that would be a binomial. But for a monomial, you can look at the degree and that's going to tell you the symmetry. So x squared is an even function, wouldn't work. Sine of x, hopefully you can kind of sketch that guy out, continue him to the other side. Same with cosine of x. Just little sketches. Log of x looks something like this, and e to the x looks something like this. Now, immediately, log and e to the x should kind of, once you get those parent functions sketched, you could kind of be able to say that's not an odd function. For sine, what you're looking for is basically it's symmetric to the line y equals x, or the idea is the opposite of x is equal to that guy. So if I have a coordinate like pi over 2, it's going to match negative pi over 2. Or your y values would be opposite. The other thing is with cosine. Cosine's an even function. You can kind of pick that up with the sketch as well. But it is good old-fashioned sine. Natural log of x minus 2 is less than or equal to 0 if and only if. The idea is you want to know when is your function below the x-axis. So you're below the x-axis kind of in this area. Now, natural log has an asymptote hanging out right here at x equals 0. So you're going to be focusing on shifts for your asymptote, and you're going to be focusing on x-intercepts. So for your asymptote, when I have x minus 2, think of that like kind of like your domain. You can say it has to be greater than or equal to 0, so x has to be greater than 2. So on this guy, we actually have shifted that asymptote over 2, and it's going to be hanging out like that. So we're looking at this region. So we now need to find our x-intercept. To find your x-intercept, you're going to take your function, set it equal to 0. Remember that has a base of e. This is in log form, switch it to exponential form. E to the 0 equals x minus 2. Solve for your x. So your x-intercept is hanging out at x equals 3. Your asymptote is at x equals 2. So it's only below between 2 and 3. We have an f function, we have a g function, and it wants to know when are these, when we compose it both directions, when are they equal to each other. So basically you need to compose the function f g of x, g of f of x. When you do your composition, these are your two answers. Set them equal to each other and kind of go from there. I just cross multiplied, and you end up getting x equals 1/3. Finding the inverse, so you switch your x and your y. Shouldn't be anything too crazy. It's a nice problem. A, B, C, D, and E are real numbers. A cannot equal 0, so it's telling you have a 7th degree polynomial. You have to decide one of these things. The idea is the rule for an odd degree function, you have to have at least one real root. So even if that's my 7th degree guy, it's guaranteed you're going to have at least one real root. Even roots, you don't have to have a real root. There's a parabola, it's an even root. It's not going to have a real root. So this is at least one real root. You have an f function, you have a g function. When you take g and compose it with f, what do you end up getting? Well, the thing is, g is just 5. So when we do a composition, you're supposed to plug in that new function for every x. Well, there aren't any x's in g to actually plug in, so it ends up just staying 5. E to the x, which of the following is an asymptote. This is why it's a good idea to know your parent functions. It's going to be y equals 0. X equals 0 would be this guy. Y equals x would be this guy. Y equals negative x would be that guy. And y equals 1 would be that guy. So it ends up just being y equals 0. It's part of the definition of an exponential function. Symmetric to the origin. Symmetric to the origin is an odd function. You want to think about transformations. If you have a C or a D, so C, draw an odd function really quick, so something like that. If I have a C, that's going to move that guy left to right, so he'd no longer be symmetric to the origin. If I have a D, it's going to move him up or down, so he no longer would be symmetric to the origin. So when you're looking at this, one of the first things you can kind of eliminate are functions that have a C or a D hanging out, and functions that have an even degree. So even degree goes away. This even degree is going to go away as well. And then you have this guy that's going to go away as well. This, what I did, I don't think I even showed you on here. I went ahead and kind of divided that out to look at it. So it looks like that. So that's a reciprocal function that now has a D that you can see. So he started off looking like this, but that D shifted him up 1 unit. Okay, so he's no longer symmetric to the origin. So basically looking at this guy, what I went ahead and did is just use the definition of an odd function to kind of verify that. You have a function f, and you're missing some information. You're missing an a and a b, the coefficients. What I tell you is f of 2 is equal to 3, so when x is equal to 2, that function is equal to 3. When x is equal to negative 2, the function is equal to negative 37. It wants to know what is a plus b. So what I did is I went ahead and I took my function, set it equal to 3, put in 2 for my x, and I got this lovely expression. Took my function, set it equal to negative 37, put in negative 2, got this lovely expression. Took these two equations, well, just kidding. Took these two lovely equations and subtracted them. Or what did I do? No, I added them in this case, sorry. So I added them. 4 plus 4 gave me 8a. 2 plus negative 2, that went away. Negative 8 plus negative 16, negative 24, there's my a. Pick one of those, plug and chug, there's my b. Just make sure that you kind of remember you're doing a plus b, you're not just doing what's a, what's b. Answer should be negative 1. Number of bacteria, this was kind of a messy one. Wasn't really, probably shouldn't have been in the pre-cal section. I think I'll talk about it actually in the derivative section. So I'll skip that one for now. 136, you have a function, it's continuous, it's defined for all real numbers, that implies continuity. Which of the following conditions has an inverse? So for a function to have an inverse, it has to pass the horizontal line test. That's your big thing. So a periodic just means that it is sine or cosine. Okay, and we kind of, if you remember from when we did sine and cosine last year, in pre-cal, you have to limit or restrict that domain for that to be one-to-one, or have a pass a horizontal line test, have an inverse. Symmetric with respect to the y-axis, that means this. So I can see pretty quickly once I draw a function that's symmetric to the y-axis that it fails. Concave up, that's another concave up, so that fails. Function is strictly increasing, so something that is strictly increasing would be something like this. Something like this. Both of those pass the horizontal line test. Function is continuous, well, sine is continuous, but it doesn't, unless it's a restricted domain, doesn't have an inverse. This quadratic is continuous, but unless you restrict its domain, it doesn't have an inverse, so it has to be D. So you're given this function. First thing I did is I rewrote it. You want to know what is the range of that function, so where are its y answers. Inverse tangent has to be in the first and fourth quadrant. So you're going to do cosine, and whatever answer you get in here, so let's say you get something like pi over 4, you're going to be focusing on just the angles that are hanging out in the first and the fourth quadrant. Well, for cosine, cosine is the base. So I'm going to focus on, I'll make it blue, oh, that blue area, that's just going to be from 0 to 1. This one was lovely. It kind of threw you with the absolute value. You should have thought about that as being plus. That should say up. Oh, that was correct. I did fix it. So you have to just kind of know your transformations a little bit and realize that it's absolute value, which is quite lovely. This one I just switched forms. So log base a of 2a, 2 raised to the a is equal to a to the 4th. So you can see that a raised to the a to the 4th equals 2a. And what I plugged in were my possible choices for a. So for this one, a turned into 2/4, so that turned into 1/2. Those were not equal, and I kept going until I found one that was equal, which would be a equals 16. One of the nice things about multiple choice, and kind of plug and check till you get there. What is the domain of this function? So for natural logs, x has to be greater than or equal to 0, and when you're talking about x, I'm talking about the stuff hanging out kind of inside that natural log. So that's stuff inside, greater than or equal to 0. Quadratic inequality, so what you do is you factor it, set it equal to 0, solve for your x's, and do that nice little sign chart, and you'll see that between negative infinity to negative 2 and 2 to infinity, that would make natural log greater than 0. Domain is given by this. What is the range? This one wasn't too terrible. You have this nice guy. It's always going to be 1 subtract something, so you're going to think about where that would start to be 0 or go into have issues, I guess I should say. And that would happen in B. 142. So this one can be a little misleading, so I would suggest if you have something with options, I would try to get a sketch if I could. So y equals x squared plus 9 is actually a circle, so I drew it out, and then I saw, well, it's symmetric to the y-axis, the x-axis, and the origin. Continuous. Just do little sketches of each of them. Hopefully you remember a tangent has vertical asymptotes. That one's going to be gone to begin with. We've seen this one a few times today, so this one is continuous for all x. And then this is what I rewrote it as. Sorry, I'm having a bad math day apparently. And the cube root function, what's nice is this is always going to be positive. A cube root of a positive exists for every single number, so that's continuous as well. So this shows the graph of the sine function for one complete period. So this time the period is equal to 2. What is the equation of its graph? Well, you can tell that the period is kind of different. We usually have 2 pi as our period. To find the period, you do 2 pi times the reciprocal of b. We know that when we did this, we ended up with 2. So what I did is I just kind of solved for what that b would be. So 1 over b is equal to 2 over 2 pi. Those go away. 1 over b equals 1 over pi. So b is going to be equal to pi. So this is going to be kind of a different looking function, but it's going to end up being one of these that has pi x. So we can eliminate all of these guys. The other thing we have to look at is where the amplitude is, and the amplitude is up at 2 and down at negative 2. So since I have an amplitude of 2, that means I have a vertical stretch of 2, which is why I would pick D and not B. Oh, this is a nice little log expression. So you have this guy. Use your laws of logs to rewrite it as 1 log. And simplify this guy out, and that's actually x squared, because this is x over 1 divided by 1 over x multiplied by the reciprocal. So you get x squared. So you're going to get e squared equals x squared when you switch forms. Take the square root of each side, and you will see that e is equal to x.